All right, Marginal Gains listeners and Marginal Gains TV viewers, really excited this morning here with James Woodcock of Bastion Cycles in Australia. Now, if you guys are not following this company on social media, you are completely missing out. These are carbon titanium bicycles, 3D printed lugs, carbon tubing, custom, like made to order. I mean, unbelievable stuff. Really beautiful. So James and I met about a year ago at the Handmade Show in Australia, and
we did
became fast friends.
Well, yeah, thank you, Josh. That's a very kind introduction. We did, yeah, crossed over in Melbourne when you were in Australia for the Hand Built Show, and when I heard that you were coming, I kind of made it my little mission to try and get you over to our small factory to have a bit of a walk through, and yeah, it's a good crossover.
Yeah, amazingly impressive. I mean, I think, well, hopefully we can get some photos and videos that we can kind of pop up, do the little magical box over the corner here. And then down below, we will put in links to the website and the social media so people can go and see it firsthand. So, yeah, so I guess, I mean, tell me how the start of this. You've got engineering in your background, like me. So how did you? Yeah. What's the transition?
Oh, look, the origin story. Yeah, it's an interesting one. The company was started by myself and two other former colleagues. So our background is automotive engineering. Actually, we're all colleagues together at Toyota. So we all had done a decade or more of designing cars, both here in Australia and also in Japan. Spent a lot of time working in Japan, and designing and developing cars to be built all over the world.
Wow.
But automotive manufacturing in Australia was coming to an end around the 2015, 2016 kind of period. Or it had been on a bit of a decline. There's the feasibility of making vehicles in Australia the writing was kind of on the wall. So as much as we were part of the technical centre, which was part of the global design resource, the manufacturing plant in Australia, which was making Camry at the time, was decided that was going to be closed down, and the technical centre where we worked also closed down. But we had 2 years of notice.
Oh wow!
I had 2 years of notice. So, and the genesis of, look, Ben, Dean and myself, we could have stayed within the Toyota family, I guess, and gone to North America or gone back to Japan. My Japanese managers called and said, "Oh, good, come back." Oh, good, you don't have to be in Melbourne anymore, just come here, what's the problem? And I'm kind of like, yeah, we are Australian though, like we like it here as well. So, but look, we travelled, all of us, and had lived overseas, and Ben and I both had young kids. We wanted to stay in Melbourne, but we're still passionate about designing things and making things, and wanted to find something that made sense to make in a developed economy like Australia. And actually the genesis story of the Bastion, our first road bike product really went like this. So Ben said to me one day, he's like, "Let's go for lunch." And it's not unusual. We went for lunch. We go to the local cafe close to work, and he starts pitching me this idea. We've been sitting down all of 30 seconds, and he starts pitching this idea. He's like, "So I've been doing a lot of benchmarking. I've been doing a lot of study. I looked at the bike industry. It's not wheels, it's not stems, it's not any of that stuff. Frame sets." I'm like, "Okay, yeah." And he said, 3D printed titanium lugs, carbon fiber tubes, custom geometry, custom everything. I think it can be done. And I looked at him and I was like, in my mind, I think, I told you this idea 3 months ago, and you've forgotten where you got it, and now you're pitching it back to me, because I had CAD already. I had started in the evenings a bit of CAD work on this concept of a 3D print, because we'd across the road from the tech centre where we were, there was CSIRO, an Australian government research organisation, had some metal 3D printers up and running, and we'd seen what was going on there and could see the potential of it. And I was playing around with the idea, but Ben had done all the business case modelling. So he'd worked out what price point something like this would need to be sold at, what the volume's likely to be, what are the competitors in the market, how much settings, really understanding, how much titanium could you feasibly put into a bike frame printed, and still have it. So, because if you give an engineer too much scope, you'll print the whole thing, or you'll. So actually, right? Yes, that's right. I never ship it. So actually, we'd independently kind of come at the same concept, but from different directions. He had a business case or a business model that worked out this is the level it needs to be at, and I had a bit of a concept going. It was clearly we were going to do it. Yeah. And this is where we still had 18 months to go until our Toyota rolls finished up essentially. Dean was brought in and added a whole lot of extra engineering firepower to the calculation side of things and simulation and modelling. And we were away. So by the time I finished at Toyota and ready to turn the lights off at the tech centre, we'd built prototypes, and I think we had built 10 prototypes, and we were at the point of selling the first customer bikes.
Wow. So in a way, Bastion was almost like a gift from Toyota to the world. I mean, to give you guys 2 years warning, that's beautiful. Yeah.
It's hard to fault Toyota on how they handle it. Like it's a difficult situation when you've got economic forces out of your control, and we bootstrapped the company coming out of those redundancies. That's how we were able to push it forward as quickly as we could. But I mean, we're also leveraging our, there's 35 years of Toyota design experience between the three of us.
Yeah.
And those kind of design principles and where we've come from for reliability, built-in quality, those kinds of, ways of thinking is how we've done it. Yeah.
Yeah, no, it's I having been there, I have to say I've never seen a company that small operate at the level that you guys operate at. I mean, the paperwork, the sign-offs, just all the little details. It's pretty amazing. I mean, I don't run my company that tightly. It's very impressive to see.
Well, that's very humbling for you to say. Thank you. But the guys at work listening to this will laugh, but I'm a bit of a fan of the check sheet.
Yes.
Bit of a fan of the check sheet. It's an interesting way it's come about, because in the Toyota world, for example, it's all it's very check sheet driven, because you need to, when you go to present your design, you need to show that you're going to avoid the water leak issue that happened in the 1979 Corolla, right? So there's a check sheet item for that. You go, oh yeah, we've got that structure.
Yeah.
And so and that's how you build in quality. Like that's how you don't make the same mistakes again, for sure. Right. But when we started Bastion, there's no check sheet for what we're doing.
Right.
So that was liberating in many ways. But you quickly realize when you're in a production environment, if you want to track what's going on and understand when something happens, or what did we do, you got to keep records of what's happened.
Yeah. So let's talk about the design. I was impressed by a ton of what you're doing, but the kind of the, I would say, the dirty secret of engineering is for all of the fancy pictures and the CFD and the FEA and like all the stuff that engineers like to talk about. Like 98% of all engineering actually happens in Excel.
Oh yeah.
And so engineers are all true Excel nerds, and I would say it's common. You get a bunch of us together, and there's generally some kind of one-upmanship with like, oh yeah, your spreadsheet can do that. Check this out, And so I was meeting you for the first time, and you were trying to explain something, and you're like, oh well, let me show you. And you open this Excel, and I just went, holy shit, that is the coolest Excel spreadsheet I've ever seen.
Well, I can't, for the one, I'll tell you about that one. I can't take credit for the kernel behind what's going on there. It's Dean's work. But
Okay.
I did have to write a reference for somebody last week in Microsoft Word.
Okay.
And I just about threw the computer across the room. I'm like, can't I do this in Excel? This is ridiculous. So, yeah, the spreadsheet that you're talking about was something we did from the beginning. We knew that we wanted to be able to calculate and simulate what the performance of the bike, this custom bike, was going to be like before we made it, and do that on a one-by-one basis for each customer. So each of our bikes is, obviously, we get a fit in from either that we do in-house through Rider Fit CC, who's a fitter who works with us, or from the dealer around one of our bespoke partners around the world. So we get a fit, but then we're adjusting the geometry for handling and for stiffness effects and the layout of the carbon fiber. So we want to be able to calculate that and show the customer what we've designed for them and how similar it is to something they know, or what, is it like an Amonda or an Avenge, or that kind of thing. So what Dean was able to develop that we still use every day of the week on the customer bikes is a 1D beam element model of the bicycle that runs in Excel. And so it's a 1D beam FEA model. So I can say that quickly, but what it's doing is breaking the bicycle up into 7 or 9 elements, including the fork, and exactly like a very detailed finite element model image you'd see with color plots of stress and displacement. We're calculating the stiffness of the bike, assuming that each beam, so the down tube or the head tube or the top tube or the seat tube, assuming each of those tubes is one beam element in the FEA mesh. And Dean has built a spreadsheet which resolves the matrix manipulation to do live FEA simulation, and we can literally type in a force 1,000 newtons at the seat, or a lateral twist, and it's calculating it live without having to press solve this FEE study and wait for the results. Because it's only 9 1D beams, it can resolve quickly, and we can actually. So this is where the Excel nodes are like this. Once you have that model running, you can then do a data table on that and run that simulation across multiple variables and do pretty crazy things. But that Excel calculation method is wrapped into our CAD model as well. So we model in Siemens NX, and it's got really tight integration with Excel. So when we design a bike, we're using that Excel tool to develop to set the geometry and understand the stiffness of the bike and how it's going to behave for handling as well. That generates a technical report, and we press save, and that setup, that data directly links back to CAD, and on the way back out, it generates the CAD model of the bike, which goes to the customer as light data as part of the package as well. So, yeah, Dean's his strength is, I like to say that I exploit Dean by setting him Excel challenges. Every now and then when I get things that I can't work out, and it happens every 3 or 4 weeks, I'm like, I'll just give it to Dean. And literally 2 weeks ago, I wanted him to calculate hoop stress in the seat post cap that we make. And in my mind, I was like, pressure, I reckon we could calculate an empirical result for that. And he came back with a spreadsheet which does way more than I expected. And you can't do this kind of business as one person. We have complementary skills that lets us do it.
Yeah, which is amazing. I think most impressive for me, there are big companies in this industry that employ, a team of engineers, and, they're going to make 5 sizes of a bike, and that is 5 CAD models that each one took, a month or 2 or 3 to really refine down, and to see the level of detail that you guys can kick out. in my mind. I mean, it's like you spent a year on the original CAD model, and then you built this spreadsheet, and all of that groundwork laid, they kind of make themselves as you go. So you're not spending a month modeling each individual bike. I mean, it's you nailed it. Yeah, leverage of time, right?
Yeah, and I developed those platforms bike at a time. The first one was done in my garage over there. Yeah. So we have a platform for the road bike, and we have a platform for the Superleggera, and we have a platform for Crossroad, and then you can throw geometry at that parametric CAD model, and like you said, there's a year invested in each one. But I mean, my background is parametric CAD within Toyota. I was a body engineer, and from early on, you get a new style surface from the stylist every 2 weeks, and we're trying to build the structure of the car inside the style surface. So you get a new style surface input, and the whole inside of the car has got to regenerate from inside that. So that's really, the CAD model's pretty. It's pretty intense. Yeah.
Wow. You're making my head hurt. I'm I'm a little too scattered. I learned early in my engineering that I am not the engineer's engineer, and I am not the type of person who can handle those problems. I have my time limits of, screw it, I'm out. I'm done. And so that's always when we started SILCA, that's one of my first the first goals was like, okay, I've got to find somebody who can solve these problems. Like you said, the complementary, complementary skill sets, because that's
you got to build up that Venn diagram of overlapping skills, right?
Yeah, exactly. Yeah. So talk to me then about getting into the 3D printing. So it sounds like you guys had, sort of some tangential contact with it across the street.
Yeah.
And then, for our listeners and the people watching, we'll throw up some images here, but these machines are, they're not small, and they are not inexpensive, and they're are wickedly complex.
So
to operate. So
all right, we're going to go down the rabbit hole from here on. So I'll try and start at the top of the rabbit hole, maybe. So what we're talking about is additive manufacturing, right? Not subtractive. So people might have a mental image of things being made on a CNC machine. You start with a block of material, and you have a cutter, and you remove the material away until you've got the thing that you wanted to make. What we're doing is starting essentially with a flat, blank sheet, and just adding material where we want to make that part, where we want to make that shape. So most people have probably seen a plastic 3D printer by now, where you've got filament coming into a hot nozzle, and you squeeze it, it gets squeezing out hot material and building up a part layer by layer. The technology that we use and what we're talking about is quite different to that. The only thing it really has in common is that it's layer-wise additive manufacturing. So we work exclusively in titanium. So we talk about laser powder bed fusion, or selective laser melting of the titanium, where we're melting a powder with a laser. We like laser powder bed fusion. It describes really what the process is. Some people talk about it being sintered metal, sintering. It's really not. So sintering is, you've got individual powder which is pressed together at high pressure, and you still end up with porosity in individual powder particles. We're really fusing the powder into a solid metal, and it's not like a forging. It's not quite as dense as that, but it is solid metal that you can machine and weld and do things with. So it's very different to plastic 3D printing, which people have more familiar with, I guess. So the machines that we run are Renishaw machines. We've got an AM250 and an AM400. Loosely, those numbers relate to the laser power. So there's a 200 watt laser in the 250 and a 400 watt laser in the 400. And yeah, as you said, they're not small machines. I guess you'd describe them as the size of two large fridges kind of put together. We've got our two machines in quite a small space, but in a room that's probably 4 meters by 4 meters. So you can work out the feet, Josh. I don't know.
So it's like roughly times 9.
Yeah.
To get a square foot from there you go.
Something like that. So yeah, not small machines. And the process goes a little bit like this. So you need to start the print on a substrate, on something. So we start with a block of titanium, and we call it a build plate. It's a perfectly flat piece of titanium, and the machine distributes a very thin layer of powder across that plate, and then the laser comes from above and fires at the plate and melts that powder to the plate. That's what starts the first layer. Now I'll come back to the process in a minute, but the powder is an interesting one. So titanium powder that we're using, it's not cheap. It's a very specific size, so 15 to 45 micron spheres. The morphology, the shape of the powder is very important because it has to flow as it gets distributed across the build plate. And it's pretty bloody dangerous. Like, it's explosive stuff because it's you can throw flour in the air, right? And it'll ignite. So we've got titanium moon dust, essentially 15 to 45 micron, tiny spheres. It's all surface area. If you get a plume of that, accidentally spilt in the air and an ignition source into oxygen, it'll explode. So yeah, somewhat tricky stuff to work with. Yeah. And there's quite a bit of, if you've got exposure to open powder, the PPE is fairly intense that you need to be wearing. So all right, so the machine runs like this. We put our flat build plate in. The machine needs to heat soak, get the build plate up to 170 degrees Celsius. It's a big enclosed box, basically. The machine does a suck down procedure to vacuum out all the oxygen, purging argon. Because essentially what we're doing is welding titanium in a big volume. So the inside of the machine has argon pumped in. Once it's down to an acceptable level of oxygen, ppm, like under 1,000 ppm of oxygen, the laser can start. And so, as I said, it's melting the powder. Then after that initial layer, there's a wiper blade which pushes powder across the plate. It will retract, dose more powder for itself. The build plate will move down 60 micron. So we print in 60 micron layers, which, I don't know, it's 12 thou, something like that.
Yeah, it's a sheet of paper.
It's quite small, 0.06 millimeter.
Yeah.
Build plate's gone down. Fresh powder gets wiped back across. The laser fires again, and all of a sudden we're fusing titanium and building up parts with powder around it. And you do that 3,000, 4,000 times, and you end up with, you've just melted the titanium in the cross section, in the areas where you want to build parts. Yeah. Yeah.
It's like the world's most expensive miniature Japanese rock garden, where you just you just keep smoothing it and then burning it. It's brilliant to watch. I'm sure you guys probably have some video or something we can throw up. But
I think there's definitely video. Our Instagram feed's got. If you go back in the Instagram feed, you'll find stuff. But it's pretty. There's some barriers to entry on doing it. I mean, obviously the cost of the machine is the obvious one, but you're consuming a lot to make it happen. You're consuming the powder, you're consuming argon, electricity, there's filters need to be changed, you're consuming isopropyl alcohol to clean the machine between builds. The substrate of titanium that we build to, you have to machine that every time to get a nice flat build. So yeah, the electricity is not
well,
we have.
But I think, so if you've made it with us this far, you're probably pretty geeky. But of course, all of this is assuming that you've designed the parts well, right? I mean, I think that's where we kind of forget, like, oh yeah, because now you are not bound by the traditional engineering textbook as to what this part can be, should be, wall thicknesses. And we'll throw some pictures up as well. But you can build porous structures within the structure. Which is a variable that really up until these technologies came about, it didn't exist before, right? You couldn't 3D honeycomb within a hollow by any other means, right? This never existed. So we're literally making this up as we go, or you as the engineer here have to make this up as you go.
Yeah, you're right. It's an amazing amount of design freedom compared to being constrained to something that needs to come out of an injection mold and have draft angle, or something that you're going to CNC machine that your parts in the machine this way and you can't machine an undercut. And because you're building up layer wise, you've got access to the inside of the part throughout the build. That's kind of what you get your head around. So we're exploiting that. Our design philosophy is really a stressed skin around a lattice. So our parts essentially are hollow. The outside skin of the part is the stressed member, and we have a lattice on the inside of the part, which does add structural stiffness, but really it's holding that skin apart, analogous to a composite sandwich panel, which is happening in 3 dimensions. So, but you got an amazing amount of design freedom that things like, oh, we need a hole here, or we need a M5 thread there. You just put it in. You know what I mean? Like it's in.
Yeah.
And we print threads. So like the through axle and then the dropouts, and it's a M12 that's printed in, the M10 for the rear derailleur hangers printed in, the M5 portions all over the place. So you can just, if you need something, it's usually less constraints to get it in the design, or you've got more flexibility than you would have with conventional manufacturing, but it's not magic. Like just like any manufacturing process, there's limitations and there's things to consider, like build orientation is super important, just like die direction in an injection molded part. So the direction you're going to orientate your part and build it will dictate whether you can have, portions build and not need support, or if you've got a wormhole going, if you've got like Di2 routing holes and things, can you design them with a shape that will self-support and not need, self-support across different throughout the part. Powder egress. So, I mean, we do a lot of hollow parts. You have to have powder egress holes so that when you recover the part, powder that wasn't fused can come out. And have those holes in acceptable places or innocuous places or low stress locations, that kind of thing. And then you get into like even the next level along from that is, okay, we're making aesthetic parts as well. Like the technology gets used pretty extensively for military application and aerospace applications for parts that are hidden within wing structures and things like that, brackets. But we make a highly aesthetic finished product. So we think about things like in the part orientation for the A-class surface, is it on an up skin or a down skin of the print? Because the up skin surface finish is going to be better than the down skin.
Interesting.
So are we printing our part this way or this way? Because what's the final appearance going to be like? So it's not, you can't,
Yeah, I guess I had never thought about that before. That's a good. That's sort of like it's like vacuuming the carpet, right? Right. It's like the pushes and the pulls are different. Tell me about the isotropic behavior of the material itself. Is it build orientation is important for support, and obviously it's important for surface, or has an effect in surface finish. Are you truly relatively isotropic, or is it Because this was an early limitation of 3D printing, right? You would have these materials that were a factor of 4, factor of 5 difference in terms of strength,
right? Yeah,
in various axes. But
certainly filament deposition stuff, the plastic stuff, the Z direction strengths, super compromised. But we definitely treat our parts as isotropic, and that is to say, I think you could, when we have test sticks to show, straight up and down test sticks at 45 degrees we've done, and actually seen very little difference.
That's amazing.
Any differences in axes in Z direction, the build direction is well within our safety factors. So one of the big, I guess, the main thing people want to know, the thing we do with each build is we do test samples with every build. So every build that goes on has a couple of test sticks which get fatigue tested and tensile static tested. So we monitor, did anything go wrong in that build, or not? It'll come out in those test samples. But from a calculation, from a simulation point of view, in practicality, we can orientate our parts any direction we want to, and not need to worry about which direction is the strongest. It's essentially isotropic. Design doesn't need to change. No. For our titanium laser powder bed fusion.
Yeah.
It depends, Josh.
Yes, it depends. Yeah. So, which I guess takes me to my next one. I think the first time I ever talked to you, you said something, and I can't even remember what we were talking about, but you threw out like, oh well, in any system where you've got hysteresis, you've got static and dynamic stiffness differences, right? You can have almost infinite stiffness, dynamically. In a high hysteresis system, and I was like, oh man, after my own heart, right? But this is one of the things that, somebody who's obsessed over this hysteresis problem for a long time, right? I mean, we are an industry that has been obsessed with weight and static stiffness for as long as any of us have been alive. And you know me, I'm not a big believer in either as being all that important. And so that's when, you throw the hysteresis problem out into discussion of this is the thing. And so, as you pitched it to me, the concept of the carbon tube with the titanium lug, it's sort of game changing, or potentially, from this dynamic stiffness point of view. So tell me, how did you bring that in with you from Toyota? Because with vehicle dynamics in my background, this is a known issue there. Say those words in bicycle engineering, and it like the room goes quiet, right? People are like, what the hell are you talking about? Yeah. So. Well,
this is definitely my business partner Ben's input and his little hypothesis on what we've got going on. But yeah, you're right. We call it KD and KS, right? The automotive people, but the KD is the dynamic stiffness constant, and the KS is the static. So yeah, like you were saying,
our coefficients, right?
Yeah, like you were saying, maybe the last podcast, maybe just the most recent podcast I listened to of yours, you were talking about it again, where if you measure something slowly, statically, our minds think that way. You push on it, it's got you can measure the newtons per millimeter and it comes back. The real world is in the time domain that's happening much faster than that. And especially when you have high frequency inputs like you would with a bicycle going over coarse chip road, you have very high frequency inputs and lots of dynamic and time domain effects going on. Ben really has put a stake in the ground, I guess, with what we think is going on, where you get in, because there's in a full carbon monocoque frame, because there's so much hysteresis and damping in the frame, you get into a loop on that. If you have a small amplitude of excitement, you get into a small loop where your effective, the effective dynamic stiffness in the diagonal across that loop. We might need to draw a sketch and put that up. It's so much higher than what the static stiffness that you measured. You measured 100 newtons per millimeter at the saddle. Over 5 seconds. But when you've got a road input coming in at tens of hertz, it behaves very, very differently. So we think, and we anecdotally, qualitatively, we have, I guess, data on the way our bikes handle and the way our bikes feel on the road, because we have the titanium at the nodes, at the lugs. We don't seem to have that same transmission, that dynamic stiffness effect coming in and having the same transmission of that road buzz, I guess, coming through. And that people describe that to us as feeling fresh after 60 kilometers or 100 kilometers that they wouldn't ordinarily. And it's like a cumulative damage problem, right? Like you get on a bike, it feels stiff, it feels fine, and you don't notice it. But when you've got those tiny little inputs coming in for 2 hours, it wears you down and wears you down. So that's qualitatively, that's what people say when they got off our bikes, that it felt smooth, and at the beginning it felt smooth at the end, and I feel like I could do another 100k. Do you know what I mean? Like, that's the feedback. We kicked off a project with a local university to try and start quantifying some of this with, a frequency study. We kind of started it, but it needs more work. Like everybody's trying to measure frequency response of bicycle frames, right? It's
these are hard problems, right? These are hard, and they require. I've been 20 years thinking about this, and the thing I've kind of boiled it down to is, the simplest version of what we call supple, right? People want to talk about supple, and I've just been defining supple recently as this very low hysteresis, but particularly, and I think when we first talked last year, we were in the middle of our handlebar tape development, where we were trying to find ever lower hysteresis foam because of this problem. You think of it, we call it the packing problem, to steal a mountain bike, it packs down. And you can see this in the foam in the bar tape, but of course over 2 millimeters or whatever, that it essentially bottoms out, and then it can never recover, and you're on this bottomed out. And this is why, it's why crappy tires ride harsh, right? Yeah. It's not a static stiffness problem. You static stiffness test a good tire and a cheap tire, and it's same difference.
Well, it's the air, right? So.
But because you're measuring the air, but dynamically, the crappy tire can't respond because the rebound damping is too high. And so, I think this is really, truly the next, in my thinking, one of the next areas to find gains in this in the sport, right? That theoretically, with less, particularly rebound damping, theoretically you're going to have less impedance, related losses in your system. You should have less at the contact points. You should have less, soreness, tingling. All those things that are hard to quantify, right? It's like the test machine can't tell you, what your hands feel like. But yeah, the theory here is interesting, and I think that the next one is this. I think we've talked before about the, Jan Heine calls it the planing effect. This, is it? We have a theory there that I've actually been working on, and I'll talk to you about after this. But that's a thing that I've got data going back 10 years that we just don't understand. Some bikes just climb faster than others, and is it frequency related? Is it stiffness related? Is it in the time, right? Is it time domain? Is it?
Yeah.
These are hard problems, and I think I love talking about it because our industry for so long has just made the 3% stiffer bike every year.
Yeah.
Right. You know, every model is 3% stiffer and 5% more aero than the previous one. And
the problems that humans can't see, right? It's the things you can't see.
Yeah.
It's the same with aerodynamics. Like aerodynamics would be easier if you could see, you know, the pressure distribution of the air going around.
Right. Right.
Yeah, you'd be like, that's no good. Like it's separated.
Yeah, exactly. We would be so distracted all the time. I would be so distracted. I wouldn't make it out of the house in the morning. Be like, well, what the hell's wrong with that?
Yeah. Honestly, I'm a bit surprised that there's no Oculus Rift add-on. You can walk into the wind tunnel and have the Oculus Rift and just see the pressure, just what's going on. Surely someone.
We just need the computing power. I mean,
yeah.
You've seen the Navier-Stokes equations. It's like, oh my God, you know, which I think is back to, you know, the thinking about your simplified FEA model. You know, I think we put so much focus on these incredibly complex solutions, and you know, the reality of you know, some of these FEA models that you see, some of these CFDs. I mean, you know, when we were running our time stepped unsteady flow CFDs, you know, you'd have 1,000 cores in the cloud computing on this thing for a day to run a single solution. Those are amazing tools, but they make it really hard to iterate through. I mean, when it takes a day to run each concept that you have in your brain, and it probably takes another day to then look at the data and begin to understand it, you just are moving quickly. And that's I think the brilliance of your Excel, when, you know, we can boil it down to this relatively simple thing and say, well, okay, this 9-beam model, and I can, you know, we can sit down together and look at 50 iterations in an hour over coffee. That's, you know, in some ways, you know, one type of engineer would say, well, it's not as valid for these reasons, but the other side of you says, yeah, but it allows us so much more investigation.
Finding the appropriate level of simulation is the tricky thing sometimes, right?
Yeah, it's that question. It's like, it depends. Does it matter? You know, my model's got 10 billion elements. Well, but does it matter?
A lot of the time in the real world, when you're developing product, all you really need to know is, are we 15% better than where we were as well? Yeah. So is it accurate to 0.5%? No, but we know that we made a change and we're 5% different. That's probably enough. Do you know what I mean?
Yeah, directionality, right? Over accuracy in a lot of these things, because even the most accurate models aren't accurate. I mean, I've never run a CFD or an FEA and then come in, shit, that's exactly what our tests say. Right.
Pretty sure anyone running FEA and then putting strain gauges on things and worrying about why they don't match, just move on.
It's a lot of time burnt. There's a lot of time burnt. So who in your team did the aesthetic design for the bike?
Me.
So well done. It's to me, that's one of the hardest challenges with the project that you guys took on. Was it's so different and new and unique, but to the I guess the unknowing onlooker, it could look like something that has been done for 25 years now, I guess 30 years now, right? It's lugged carbon bike.
A mixture of traditional but modern technology. So like a traditional aesthetic. I mean, we're on round tubes, but it's a lugged bike, but it's unmistakably modern as well. And it came about two kind of factors, where we are 3D printing the lugs. So from my point of view, I felt like we've got the design freedom. We'll put some character into it. Do you know what I mean?
Yeah.
Like, why not? It's design, you know, it's for free, basically. We need to make this bracket. They're fancy brackets, actually.
Yeah. We
need to know. Everything's a bracket. So we need to make this bracket which connects the down tube to the head tube. I could probably do it in about 45 seconds in CAD if it's just two tubes. And with filleted together. but with the thing, it's not going to cost any more really for it to look like something. So yeah, we invested time in giving it character and having a distinctive look. But then the second aspect is the thing needed to run in a parametric CAD model without a stylist being in the way. So early on, I actually had some styling guys, automotive styling guys from General Motors come in to have a look, local guys, and I'm like, wow, that's it's pretty cool. And like, who does the style surface? I'm like, mate, I've eradicated your role. It's just straight to engineering services, and the thing runs. So, I mean, as we evolve as a company, we'll need to progress, mature, I guess, our styling and our design language a little bit. But fundamentally, we're building custom bikes that need to be parametrically driven. Yeah, there'll be a style image at the beginning of the platform development, but then it exists in hard CAD. Yeah.
I think it's hard for the non-doer. It's hard for me to put into words how complex everything you just said. That's really beautiful mathematically in the back end, and incredibly hard to actually execute. I mean, it's one thing, we all talk parametric models and you change a dimension, the whole model changes through, but to actually keep your design language, not nuke the model, right? Because we've all been there. I can go up to 6, but it's 6.1. It's like you reboot the machine. But to keep the design language in there, because it's built not into the styling, but it's built into the engineering. I love it. I mean, that's beyond.
It's very kind of you to say.
Well done.
Well, it was very kind of you to say. Thank you. I feel lucky that we've, as I said before, bootstrapped these engineering jobs for ourselves. Where, like, if my wife says, "What are you doing tonight? Are you watching TV with me, or are you working?" I'm like, "Oh, working," because every day I wake up and feel stoked that that's what we're working on. Developing those kind of products and developing those designs.
It's awesome. Just awesome. Last one, I know you guys also do kind of like consulting. There's a performance side of the business. Is that something you can talk about?
Yeah, I'm happy to talk about it a little bit. So that's really, we don't actively promote it, but it's come organically from the Bastion Cycles business. Obviously, people seeing what we're doing with the bikes, and we've been involved with a number of different projects. There's quite a few track cycling parts that we've developed, either available or soon to be available. We've done stems and custom bars and Madison specific bars for the Madison event, cranks, a few Paralympic cyclists we have on our kit as well. So we support a hand cyclist from Melbourne, Stuart Tripp, who rides a custom hand cycle that we've built, which has got 3D printed titanium fork and a carbon fiber monocoque tub. And another athlete, Carol Cook, rides an upright tricycle, and we've developed an aerodynamically optimized rear axle for that, same using our technology. So 3D printed titanium fancy brackets with carbon fiber, aerodynamically optimized carbon fiber cross beams and that kind of thing. So those projects have come about, and it's great to be able to work on that stuff. But we also print parts for other bike builders and other companies. We have a fair bit of print capacity now in titanium with our 2 machines running, and we produce parts for Prova Cycles and Sturdy Cycles in the UK, and a number of a number of others. People send us their data, and we can quote it out for how much it's likely to cost. We take people's essentially napkin sketches. We can develop that up to a printable part, all the way from that level to people saying, "Just print this, please. Here's the data." So yeah, that side of the business is kind of naturally, organically growing.
Awesome. That's super cool. So if anyone out there needs anything, call James. They can make it for you. Really
engineering at bastionadvance.com is for that one. But anyway, we'll put some links up.
Yeah, no, we'll definitely get them from you and put them below, and throw up some photos and links to the social so you can go see what we're talking about. Beautiful stuff. Beautiful stuff. Well, James, this was really a pleasure. Thanks so much for your time, and really just awesome talking with you and hearing what you're up to.
Not at all. Well, thank you for the opportunity. It was great to see your face again, and nice to have a chat. And I look forward to you coming to Melbourne again one day.
Yeah, I look forward to going anywhere again someday.
Yeah, hang in there.
Yeah. All right. Well, all the best, and we'll talk to you soon. Cheers.
Yes. Thanks, Josh.